We're happy to have Laura Holt as our speaker today. She came from all the way across the parking lot in Northwest Research Associates. Laura graduated summa cum laude from St. Cloud University with a double major in math and physics, and then came here to grad school at CU, where she worked at LASP with Cora Randall, and she's been studying the quasi-biennial oscillation and atmospheric dynamics. So she's going to talk to us today about gravity waves in the global 7-kilometer GEOS-5 Nature Run.
Thanks, Mike. Can everybody hear me? Okay. All right, good afternoon, and thank you everybody for coming today. Today I'm going to talk about gravity waves in this 7-kilometer GEOS-5 Nature Run. And this is work that I did as a postdoc, working with Joan Alexander. And we also had a lot of collaborators at NASA Goddard: Larry Coy, Bill Putman, Andrea Malad, Stephen Possum, and Max Suarez. So this picture in the background shows the visible clouds from the Nature Run on July 1st. And even with 7 kilometers, we still don't have a cloud resolving model yet. And so local updrafts and deep convection aren't explicitly resolved yet. However, the mesoscale organization of those systems is beginning to be resolved. And so you can see some of that in this image. So we've got some broken marine stratocumulus over here. There's some shallow convection going on over the Amazon. And there's also some organized convection in the ITCZ, as well as in the large-scale mid-latitude cyclones. So models like the Nature Run are in what's called the gray zone, which is where some of the processes that are traditionally parameterized by GCMs have started to be resolved. So things like convection and gravity waves start to be resolved. However, these processes aren't fully resolved, and even with increases in computing power and the accompanying increases in resolution, climate models will be in this gray zone for the foreseeable future. So we will continue to need to rely on parameterizations, but at this time they are poorly constrained by observations, and this is due to several factors. For example, we have limited time and space observations. We also have instruments being subject to the observational filter, and we have the fact that gravity wave drag remains a considerable challenge to estimate from observations at this time. And these contribute to biases in the simulated winds and temperature in models, especially in the Southern Hemisphere stratosphere. And so at this time, we can use high-resolution models because they provide global distributions of things like the vector momentum flux, the associated gravity wave drag, as well as some gravity wave sources. And we can use these to inform our gravity wave parameterizations, which leads to some less arbitrary tuning of the parameterizations, which can be quite maddening, as those of us who have spent some time tuning gravity wave parameterizations know. So our goal is to use the high-resolution Nature Run to assess the small-scale waves, their sources, as well as their effects on the large-scale winds. And we are going to focus on two topics that are of interest in the research lately, and that is tropical convection and waves and their effects on the stratospheric mean circulation in the QBO region, and then extratropical gravity waves and their sources in the Southern Hemisphere winter. So the Nature Run is a 2-year free-running climate simulation. It was initialized with MERA winds, and it has prescribed sea surface temperatures and emissions. It's a fully non-hydrostatic run, and it was run with a cube sphere, finite volume, dynamical core. They used second-order divergence damping, which is an issue that will come up again later. And it has 7-kilometer horizontal resolution, which puts it firmly in the gray zone. And what that means basically is that things like the orographic gravity wave parameterization and the convection parameterization are what's called scale aware. So as the resolution is tuned down, these parameterizations themselves do less and less, and the resolved processes do more and more. This is what the vertical velocity near 20 kilometers looks like in the Nature Run. This is just for one day in January that I've looped over. So you can start to see all these small-scale gravity waves in the tropics. There are some waves that are coming off of some islands, and you can see a lot of orographic gravity waves over the topography, as well as some planetary waves in the Northern Hemisphere here.
I'm sorry, could you point out the orographic waves again?
So there's some over the mountains here. You can see how they're stationary over the Rockies. There's some over here, over here, over here.
Yeah, thank you.
Yeah. So this is what the vertical resolution of the Nature Run looks like. In the stratosphere, it's basically 1 kilometer and higher. And in particular, in the QBO region, it ranges from about 1 to 1.3 kilometers. So the rest of the talk is going to be guided by these 3 questions. So number 1, how realistic are small-scale gravity waves and convection in the Nature Run? And to answer that, we're going to compare gravity wave momentum flux to other models and balloon data. We're going to compare the Nature Run gravity wave properties to those from the AIRS instrument, and then we're going to compare Nature Run precipitation to observations from TRMM and GPM. Question number 2, how do gravity waves contribute to the QBO forcing in the Nature Run? We're going to answer that by quantifying and evaluating the gravity wave forcing on the mean flow in the QBO region. And finally, number 3, what mechanisms are generating the non-orographic gravity waves in the Southern Hemisphere winter extratropics in the Nature Run? And to answer that, we're going to relate tropospheric sources of gravity waves to the gravity wave momentum fluxes in the lower stratosphere. So question number 1, start by comparing the gravity wave momentum fluxes. So to estimate the absolute gravity wave momentum flux, we've used this equation from this Geller comparison from 2013. And in this case, all the primed variables are scales that are less than 1,000 kilometers. And so this is what the Nature Run January average of the absolute momentum flux looks like at 20 kilometers. So it's January, so the Northern Hemisphere shows more flux, and the highest values are over the orographic regions. And compared to some other estimates from this Geller comparison, we have several models here. So the Kanto model and the CAM model are high-resolution simulations, and the other 3 are coarse resolution simulations that have parameterized gravity wave drag. And what's shown is the parameterized gravity wave drag in these 2. The Kanto model didn't have orographic or non-orographic gravity wave drag parameterized, and CAM only had orographic parameterization. Kanto, I think, was half a degree horizontal resolution and 300 meters vertical, and CAM was a quarter degree horizontal and about a kilometer or more vertical in the stratosphere. And so the average values for each panel are shown on top here. You can't see that very well. It says about 6, about 0.6, 3, 3.5, and 4 millipascals. And so the Nature Run comes in at about 1.3 millipascals. And that's sort of on the low end, especially when you look at the high resolution models. But overall, the global variations are very realistic, and we're really happy with that. And let's see, the July absolute gravity wave momentum fluxes tell a similar story. So we've got the large fluxes over the peninsula, Antarctic Peninsula, and in the southern tip of South America. The same in the Nature Run. And again, the global variations look good, and the mean values are a bit on the low end. So this slide is now adding bore-core balloon data with the models that were shown in the previous slide. So if we look at, this is October now, and the Nature Run looks pretty good over the peninsula compared to bore-core, and it looks better than actually all the other models. And so overall, the values are a bit low, but the global patterns, again, look very realistic. So moving on to comparing the gravity wave properties with those from the AIRS instrument. So for the next several slides, I'm going to be showing comparisons of the Nature Run and AIRS brightness temperature anomalies. And so for the anomalies, we're taking those to be scales less than 500 kilometers. And so this is what the AIRS brightness temperature anomalies look like for July 26th. And you can see all these small scale gravity waves over the peninsula again, and southern tip of South America, and then non-orographic over the ocean. And so to get the Nature Run brightness temperature anomalies, we sampled the Nature Run at the AIRS locations, and then we used the AIRS averaging kernel to obtain the brightness temperature. And so you'll notice that the scales are different here. So the Nature Run gravity wave amplitudes are smaller than AIRS, and it's also missing some of the smallest scales. But in general, the patterns and the sources look good. So first we picked out the events to compare. So in order to get the gravity wave events, we had to choose a threshold. For AIRS, we chose 3 times the noise. And for the Nature Run, it's a somewhat arbitrary choice, but we chose 0.02 Kelvin. And we tried a bunch of different thresholds, and that didn't seem to affect our conclusions too much. So I'm just showing one of those here. So this is showing the thousands of events for AIRS and the Nature Run that were for the month of July. And you can see that, again, the global patterns are very similar, and the absolute number isn't going to be the same, again, because it relies somewhat on this arbitrary choice of the threshold for the Nature Run. So this is now showing comparing the amplitudes from AIRS and the Nature Run. And so you can see that they both show, again, very similar patterns in where the large amplitudes are. Again, the scales are different. So the Nature Run has amplitudes that are about 5 times smaller than AIRS. And this seems to be typical of climate simulations. So it's not that unusual. And yeah, again, the global patterns do look very good. Looking at the wavelengths for, again, AIRS and the Nature Run, they both show lower wavelengths over the peninsula and the southern tip of South America, again, and some smaller wavelengths over Antarctica. Again, though, the wavelengths in AIRS are about 2 times smaller than in the Nature Run. And finally, looking at the propagation direction of the waves in AIRS and the Nature Run. Again, so the pink colors are showing propagation to the northeast or southwest, and the blue colors are showing propagation either to the northwest or southeast. And we can kind of break this arbitrariness by considering what the background winds are doing. So since this is July, we have winter here, and the winds are going to be westerly. And so if we assume that the waves are propagating against the background wind, then we would have waves propagating to the southwest that are pink and to the northwest that are blue. And so we've got propagation into the jets, which has been shown in some previous studies. So finally, for this question, we're going to compare some Nature Run precipitation to observations from TRMM and GPM. So first, we compare the Nature Run to TRMM, and this is in the tropics, so from 10 south to 10 north. And these are frequency wave number spectrums, where the convention here is that westward propagating waves have negative zonal wave numbers and eastward have positive zonal wave numbers. And so you can see that overall, the pattern looks quite good for the Nature Run, and especially that it reproduces this preference for westward propagating waves. So if we look at the precipitation spectra now with the background removed, so the Wheeler-Collattis type plots, we can compare the preferred modes of the Nature Run to those of TRMM. So looking at the antisymmetric modes, you can see that the mixed Rossby gravity waves are here in the Nature Run, and the Kelvin waves here, and inertia gravity waves as well. Now this is the probability distribution of the Nature Run tropical precipitation compared to the TRMM precipitation. And so what you'll see here is this is low precipitation rates over here, and the Nature Run is higher than TRMM. And this tends to occur in global models where we tend to see a lot of drizzle. And then in the middle range of precipitation rates, the Nature Run is a little bit low compared to TRMM. And then at the very highest rates, the Nature Run is actually higher than TRMM again. And this is relevant because we think that these intermittent precipitation rates are producing large amplitude gravity waves that are important for the lower stratosphere. So now switching from the tropics to the Southern Hemisphere extratropics, this is the probability distribution of July precipitation compared to GPM now. And this time we've broken the PDF into orographic and non-orographic regions. So that's shown here, where the gray denotes orographic regions. And what you can see is that for the GPM is in black and Nature Run is in red here. And what you can see is that for the non-orographic precipitation, the two actually agree remarkably well. So to recap question 1, how realistic are the small-scale gravity waves and convection in the Nature Run? So we showed that the global pattern of gravity wave momentum flux in the Nature Run compares well to other models, but the global means are on the low end. We showed that gravity wave momentum flux in the Southern Hemisphere compares very well to Vorkor over the peninsula, but is weaker on average. We showed that the Nature Run is similar to AIRS in global pattern, but the Nature Run waves are smaller in amplitude and longer in wavelength. And the Nature Run reproduces a broad range of convectively coupled waves in the tropics, and the non-orographic precipitation agrees remarkably well with GPM in the Southern Hemisphere July. So moving on to question number 2, how do gravity waves contribute to the QBO forcing in the Nature Run? And to answer that, we're going to quantify and evaluate the gravity wave forcing on the mean flow in the QBO region. But first, I have a few background slides on the QBO. So the QBO is this oscillation in tropical lower stratospheric winds where about every 28 months or so, the zonal mean winds change sign. And we know that the QBO is driven by a continuum of waves, all the way from large-scale Kelvin waves to small-scale gravity waves. And the details of the spectrum are still not very well understood. But we do think that more than half of the forcing is due to gravity waves that must be parameterized by GCMs in order to obtain a model QBO. And we also know that model QBOs are very sensitive to the changes in many parameters, including resolution, and even things like choice of dynamical core, and especially the gravity wave parameterization. So why do we care in the first place about having a QBO in models and having it right for the right reasons? These are just a few examples. So the QBO influences tropical, extratropical teleconnections, and also seasonal forecasts of the NAO and tropical cyclone activity. And differences in wave forcing and or QBO winds in the lowermost stratosphere could affect tropical upwelling. And finally, how will the QBO change with a changing climate, and what are the implications of this? So there are a few studies that suggest that the QBO will change with changing climate. This is just one of them. This is Kawatani and Hamilton. And they showed observational evidence that the amplitude of the QBO at 70 hectopascals might be decreasing with time. And they were able to confirm that in some of the CMIP-5 models that did have the QBO. And so this is consistent with the increase in tropical upwelling that the CMIP-5 models predict with the warmer climate. This is another study that highlights some of the challenges in predicting the changes in the QBO with a warmer climate. So this is a study by Scherber and colleagues where they looked at the change in the QBO period with very subtle changes in the gravity wave parameterization. So this is phase speed and the gravity wave drag. And so you can see that you can barely tell the difference between some of these lines. Like the orange and the red are overlapping, and then this dashed one. And they led to drastically different predictions in the change in the QBO period. So this is the control, and this is the 4 Kelvin increase run, and again with a different parameterization. And then this one barely predicts any change at all in the period. So now we're going to quantify and evaluate the gravity wave forcing in the Nature Run. This is what the QBO looks like in the Nature Run. So this is the Nature Run on the top and compared to the MERA-2 QBO on the bottom. And so the Nature Run, as I said, was initialized with MERA winds. And so this is kind of a test that the Nature Run can sustain the QBO. And it looks pretty good compared to MERA-2. Its period is slightly shorter. But then on the right in these panels is showing the winds averaged over the positive phase of the QBO and the negative phase of the QBO. And then on the bottom, I've overplotted the Nature Run in the dashed lines so you can more easily compare. And like MERA-2, the Nature Run shows a slightly stronger winds in the negative phase of the QBO than in the positive, but overall it's a little bit more symmetric than the MERA-2. And yeah, that's all. So here's what's actually driving the QBO. So this is the Nature Run parameterized gravity wave drag on top and the EP flux divergence from the resolved waves on the bottom. And so you can see that even with the 7-kilometer horizontal resolution, we still are relying on parameterized gravity wave drag to largely drive the QBO, which is somewhat surprising to us. And so yeah, the parameterized gravity wave drag is something like 3 times larger than the resolved EP flux divergence. But we can still look at the resolved gravity waves and see what they're doing. So this is showing the vertical EP flux, sorry, that shouldn't say vertical. It's just the EP flux divergence from different wave number and frequency bins. So this is the total EP flux divergence, which was shown on the previous slide. And then the second panel is showing just the westward small scale waves, which are defined by wave numbers greater than or equal to 12. And then this is the westward large scale waves. And the fourth panel down is the eastward small scale waves. And finally, the last panel is the eastward large scale waves. Sorry, did I say large scale here? Small scale, large scale. And so what we can see here is that during the westward phase, or westward shear zone, we have westward small scale waves dominating. Whereas in the eastward shear zones, we have the large scale waves, the Kelvin waves, are contributing a little bit more than half, and the small scale waves are making up for the rest of it. And this is in agreement with what some previous studies using high resolution models have shown. So now if we look at the EP flux divergence averaged over positive and negative shear zones, we get the solid lines here. But if we look at the EP flux divergence where we just take the negative EP flux divergence over the negative shear zones and the positive EP flux divergence over the positive shear zones, then we get these dashed lines here. So what we can see, and what we could kind of see in these plots, but it wasn't as obvious, is that there's, even in the negative shear zone, say, there's still a lot of red stuff going on here. And for example, in the positive shear zones, there's a large blob of negative EP flux divergence, and there's not as much here, but it's still there. And so what we think is going on is that there's basically a large amount of cancellation that's happening in both shear zones, and it's not being as scale selective as we'd like it to be. So this is now comparing the EP flux divergence to, and also the gravity wave drag, compared to MERA2 total zonal forcing. So this part of the momentum equation. So if we assume that what MERA2's QBO is doing is basically what's happening in observations, then in order for a model to simulate a QBO, it should basically have gravity wave drag and resolved EP flux divergence equal to these terms on the left. And so for MERA2, that term is the solid lines, and then the gravity wave parameterization, the gravity wave drag for the Nature Run is the dashed lines here, and the dot dash is the total. Yeah, obviously. Oh no, this is the dot dash, sorry. And then this is the total. So basically what you can see is that the parameterized gravity wave drag is roughly equal to this. And so combining that with the resolved waves, it actually results in a little bit more than what MERA2 shows, and maybe that explains why the QBO period is slightly shorter in the Nature Run than it is in MERA2. And one last observation here is that if we look at the numbers here, so the dashed lines here, roughly at 0.2, that's roughly where the MERA2 forcing is. And so perhaps if the Nature Run didn't have such a large amount of dissipation going on, then the gravity wave drag could be tuned down. And so this is showing the kinetic energy spectrum for the Nature Run. And basically for the large scale waves, it follows the n to the -3 law that's been noted in observations. But then when you get to the region where we expect it to follow this n to the -5/3, the spectrum in the Nature Run abruptly falls off. And this is characteristic of models that have very large dissipation at the smallest scales. There's also some evidence that the dynamical core can influence the ability of the model to have a QBO. And so this study by Yao and Jablanowski showing idealized dry dynamical core simulations where all they did was change the dynamical core. So semi-Lagrangian and finite volume, Eulerian and spectral element. And the only core that wasn't able to maintain the initialized QBO was the finite volume. And also they showed that the measures of wave activity in the finite volume dynamical core were much lower than in the other versions of the model. So we also have vertical resolution to look at. So this is a study by James Anstey and colleagues showing that if you have a model where you just look at the EP flux divergence as a function of altitude and time, where the winds are shown in the colored contours and the EP flux divergence is shown in the filled contours. So just by increasing resolution, increasing resolution, they were able to get more EP flux divergence in the shear zones. So we also did a little experiment of our own to look at the effects of resolution on the EP flux divergence. So this is showing zonal wind in the left panel as a function of pressure. And so we had a control run where we had 1 degree horizontal resolution. We had a doubled vertical resolution run with 137 levels and still 1 degree horizontal resolution. And we have the nature run, which is a horizontal resolution increase by 16 times to 0.0625 degrees, and the 72 vertical levels still. And so we picked times where the zonal wind profile was the same in all three so that we could compare the EP flux divergence. And you can see that for the nature run, basically increasing the horizontal resolution leads to 4 times increase in the divergence near the zero wind line. So here. And then doubling the vertical resolution leads to a doubling of the EP flux divergence. So you kind of get more bang for your buck by increasing the vertical resolution. Okay, so recapping question 2, how do gravity waves contribute to the QBO forcing in the nature run? So high frequency, small scale gravity waves tend to dominate during the westward shear phase. Kelvin waves provide half of the forcing in the eastward shear phase, and the other half comes from gravity waves. The resolved waves in the nature run contribute about 1/4 of the zonal force for the QBO, and so we still need the parameterized gravity wave drags to get a QBO. And we talked about how this could be because of too much dissipation in the model. It could be the dynamical core, and it could be because of vertical resolution. Okay, so moving on to question 3. What are the mechanisms generating the non-orographic gravity waves in the Southern Hemisphere, winter extratropics in the nature run? And to do that, we're going to relate tropospheric sources of gravity waves to gravity wave momentum fluxes in the lower stratosphere. But first, again, a little bit of background on this question. So extratropical non-orographic gravity waves. In the current paradigm of gravity wave parameterizations, modelers tend to think that orographic gravity waves directly influence the stratosphere, and the non-orographic gravity waves are important for driving the mesosphere. There are a few climate models that tie the parameterized gravity wave, non-orographic gravity wave drag to sources in the troposphere, but still they tend to follow this paradigm where the fluxes for the non-orographic gravity waves are important in the mesosphere. However, there's been recent observational evidence that shows that large amplitude, localized, intermittent gravity wave, non-orographic gravity wave events are likely forcing the lower stratosphere directly. So, for example, this is a study showing the gravity wave distribution, the distribution of gravity wave momentum fluxes. So this is momentum flux, and this is occurrence frequency. And in the thin lines is from the Concordiasi balloon data. You can see that they both, the black one is orographic gravity waves, and the red one is non-orographic, as they've divided it up here. And so they both follow this sort of log normal distribution, and the orographic gravity wave momentum flux shows, a higher tail, a larger tail than the non-orographic gravity wave momentum flux, but the non-orographic gravity waves are over such a large area that at times the non-orographic gravity wave drag can contribute as much as the non-orographic gravity wave drag. So some recent studies, like this one by Wei and Zhang, show the importance of moisture in the ability of a model to produce gravity waves. So this is simulations of an idealized baroclinic jet where all they've done is increase the relative humidity in each simulation. And the color contours are showing gravity wave emission. And so you can see that in the simulation with the highest relative humidity, they got the largest amount of gravity wave activity. And then here's another study showing the importance of moisture in non-orographic gravity wave activity. So these are WRF simulations over the Southern Ocean. And so this is height and this is distance. And this is the dry simulation and this is the moist simulation. And you can see that in the moist simulation, the gravity wave activity is much stronger. And they concluded that the run with the moisture was able to reproduce more realistic gravity waves. And finally, this study by Stefan and colleagues shows that convective gravity wave drag in the summer extratropics can have a large impact on the lower stratosphere. So they took WRF simulations and they forced them with observed latent heating from radar precipitation data over the continental US. And then they looked at the gravity wave drag produced by those waves. So the purple one is showing the gravity wave drag that was produced in WRF, and then they compare that to the CAM, total gravity wave parameterized drag. And you can see that in the lower stratosphere, especially, the convective gravity wave drag from the WRF simulations is like an order of magnitude larger than the CAM total. And in general, this is the breakdown of what the CAM parameterized gravity wave drag looks like. Like I said earlier, the paradigm is that in the lower stratosphere is where the orographic drag is important, and then in the mesosphere is where the convective drag is important. But again, these simulations with WRF have shown kind of a different story there. Okay, so now relating some tropospheric sources of gravity waves to gravity wave momentum fluxes in the lower stratosphere. So the next few plots I'm going to show are from this paper that we've submitted. And this plot is showing the gravity wave absolute momentum flux at 15 kilometers for one day in June. And so it has been binned to 10 degrees by 5 degrees. And so the idea is, can we relate diagnostics of tropospheric gravity wave sources to this gravity wave momentum flux in the lower stratosphere? So this is just showing a couple of different examples of what we're trying to do. So the blue contours are just showing precipitation, a certain threshold that we picked, and the fronts are shown in red. And the results weren't that sensitive to the threshold that we picked. We just kind of picked it so that there would be similar areas contained by each contour for both precipitation and fronts. So as you can see, they tend to occur where the maxima in gravity wave momentum flux is occurring. And so we're just looking at non-orographic sources. And so the orographic sources here aren't included. But yeah, in general, they tend to coincide with these blobs of momentum flux. And precipitation and fronts sometimes coincide. It seems like on average, maybe they coincide more often than not. And then we compiled statistics on these events. So how often do these occur together? So how often does precipitation occur where there's a maximum in gravity wave momentum flux? And so that's what is shown here, and then the same for fronts over here. And so for precipitation, there's kind of a uniform ring at mid-latitudes. And for fronts, it seems to be they're more correlated, maybe from 45, and then they kind of spiral into the pole, all the way over to almost to the peninsula here. And then we've got this large area over the southern Pacific Ocean that seems to be really important for precipitation. And then if we look at the average, so this is now the June, July, August average of gravity wave momentum flux in the colors, and then the averages of the precipitation and fronts, the thresholds again, in the colors. And so this tells a similar story again, that precipitation and fronts are both important from basically from 45 west, and then it kind of spirals in to the Antarctic Peninsula. And then we've got this large area over the South Pacific again that seems to be really important for precipitation. And what I've also plotted here is in the dashed line is where the precip exceeds 10 millimeters per hour, 0.2% of the time, which doesn't seem like a lot, but again, these are sporadic, large amplitude events. And so the intermittent events seem to be very important again over the South Pacific. So now if we look at the zonal mean of these quantities, so on the top there's the zonal mean of the absolute momentum flux, non-orographic again. And then the middle panel shows the precipitation, and the bottom panel shows the frontogenesis function. And so what we see is that there's two peaks in the zonal mean momentum flux, one at 60 and one near about 30. And the one at 60 seems to be associated with fronts and precip. And then the one at the 30 degrees south is associated with the intermittent precip events mostly. And if we look at, so this was the absolute momentum flux at 20 kilometers. And if we look at what it looks like at 15, or sorry, this was 15, this is 20. We notice a huge decrease in the peak at 30. And so we can conclude that these high amplitude gravity waves that are being generated from the intermittent precipitation are breaking in the lower stratosphere because most of their momentum flux has been absorbed by the time we get to 20 kilometers. So, yeah, the peak at 60 is associated with these, and the peak at 30 is associated with intermittent precipitation. And now if we compare the non-orographic gravity wave momentum flux to the orographic gravity wave momentum flux, this is the zonal mean again. And so the total flux is the dark black line, and then the orographic is the solid gray, and the non-orographic is the dashed gray. You can see there's two peaks in the total momentum flux, one at high latitudes and then one at mid latitudes. And the high latitude peak seems to be completely dominated by the orographic flux. And then there's a smaller peak in the non-orographic flux that we saw on the last slide at 60. But then at the mid-latitude peak in the total flux, there's more than half of it is coming from orographic, but there's still a very large proportion of the peak that's coming from non-orographic gravity waves. And it's almost 40% of the total. Okay, so recapping question 3, what mechanisms are generating the non-orographic gravity waves in the Southern Hemisphere winter extratropics? So precipitation shows the strongest correlations with gravity wave momentum flux for July, highlighting the importance of convection as a gravity wave source. We showed that intermittent strong precipitation events contribute almost 40% to the total mean zonal momentum flux. And finally, latent heat and convection is an important source of waves not only in the tropics and extratropical summer, but also in the Southern Hemisphere wintertime storm tracks. And that brings me to my conclusions. So we looked at the global pattern of gravity wave absolute momentum flux and found that it looks good in the Nature Run compared to both other models as well as to balloon data, but the mean values were tended to be on the lower end. We showed that the Nature Run is similar to AIRS in global pattern, but that the Nature Run gravity waves have smaller amplitudes and longer wavelengths. We showed that resolved small-scale waves in the tropics are well represented and behaving realistically in the Nature Run. We showed that resolved waves in the Nature Run contribute about 25% of the zonal force for the QBO, but we still need parameterized gravity wave drag to get the QBO. We showed that high-frequency small-scale gravity waves dominate during the westward shear phase of the QBO, and that Kelvin waves provide about half of the forcing in the eastward shear phase of the QBO, and gravity waves make up about the other half. And we looked at Southern Hemisphere sources and found that convection was an important source of large amplitude gravity waves that break in the lower stratosphere, and that those gravity waves contribute almost 40% to the mid-latitude peak in zonal mean total momentum flux. And that's all I have. So thank you.
You mentioned that you were going to come back to the question of the importance of divergence damping in the models, and I guess I missed it. So is that a significant feature in perhaps the underestimate of gravity wave momentum fluxes?
Yes. So I should have mentioned it more explicitly, but sort of here, I guess, is where we came back to it. So yeah, the second order divergence damping is probably contributing in large part to this fall off. And we had some other runs where we looked at like a fourth order divergence damping, and they did extend the tail a little bit more like that. So yeah, we think that the divergence damping is probably too strong.
So your vertical resolution is not that high. Do you think that you're getting all the Kelvin waves that should be driving the QBO? I mean, you said half of the eastward momentum forcing was from Kelvin waves, but those Kelvin waves in the lower stratosphere have really shallow vertical resolution, vertical wavelengths, and they're slow. Mm-hmm. Did you compare to see if you have? I guess they're hard to observe also because of the vertical scale, but I wondered if you think you have them all.
Well, I don't know, but I guess, so we think that the Nature Run is doing a good job of generating tropical waves, as evidenced by the comparison to the precipitation spectrum. I think the problem probably more lies in, like you said, their small vertical scale. And so, when we looked at the plot, this plot, they're contributing up to half of the forcing in the eastward shear zones, which is what we think they should be doing. It's just that the overall magnitude is much smaller than we hope it should be, and we think that that's because, they're either breaking too low because of the vertical resolution, or they're being damped excessively. Yeah.
Thank you.
Just to follow up on that question, with WAGON, we are running it at 110 vertical levels now. And in particular, between the boundary layer and about 30 kilometers, we are maintaining a 500-meter vertical resolution. Makes a huge effect on the QBO, especially simulation of the QBO below about 40 or 50 hectopascals. Depends on resolving very small vertical wavelengths, slow Kelvin and Rossby gravity waves. If you don't have that resolution, you will not get those waves. You're talking just about a few kilometers vertical wavelength, and especially using a finite volume scheme. I mean, they're just not there. So when we run a 1 degree, 500-meter resolution, we get a much nicer QBO with something that, it looks very much like the observation. So I think that's an important part of it as well.
Yeah, I mean, most models can't, especially have problems in the lower levels of the QBO.
Right. So that's the only point following up on what Ann said, that I can confirm that vertical resolution matters a lot for the simulation in the lowermost stratosphere.
So I was wondering if I can ask two questions. Okay, the first question is, you showed a precip intensity spectrum, and I was just wondering if that had been put on the same horizontal grid, so that you showed that the Nature Run had much higher intensities than TRIM.
This plot right here?
No, even further back.
Are you sure? I think that's the first precip plot.
Yeah,
That one?
That one, right?
This one?
Yep.
Yes. So for this plot, I think so. Andrea made this plot, and I believe she sampled the Nature Run like TRIM.
Okay, so the Nature Run really is already producing more strong precipitation and still has weaker amplitude gravity waves.
Right.
Okay.
So it's not, yeah, right. That is a puzzle, a bit of a puzzle. So it's probably that it's not producing them it's not producing the right sort of duration of event or something. Yes.
And the other question was just, are you possibly missing, well, even in the waves at the end that you're calling frontogenesis generated waves, is it possible that sort of non-precipitating shallow convection could be playing a role in those waves as well?
Non-precipitate, so, I mean, there's
Yeah, in this
one?
stuff. Yeah.
So you're saying in the areas with the fronts, it's not, precipitation, I mean, it's just a proxy for convection, but there could be convection going on that's not related to precip?
There could be,
That I'm not.
Shallow convection where the precipitation evaporates before it hits the ground, or...
I didn't look at any other measures of convection. Be a good idea, though.
Any more questions? Yeah.
You only got 2 years, but did you look at the breakdown of the Southern Hemisphere vortex?
A little bit. I mean, I haven't studied it in depth, but there were some plots of it that I saw, so I think it is late, as in most climate models. That's about all I remember.
Since you have that map in there, I'm usually thinking that fronts and precipitation come together over the ocean. I mean, what else is there to generate precipitation there? And so it's interesting, this area in the Pacific, around mid-latitudes, where flux is associated with precipitation, but not with fronts. How exactly does that work? I mean, there is precipitations, but there is no fronts, or that's obviously not the right interpretation, but how do you
that's a
interpret
question
that?
I've gotten many times. Yep. People have said that they think of fronts and precipitation going together. So what's going on? And all I can say is I guess that the nature run shows something different, that it's not always the case that they go together. And especially not when you have maybe these intermittent bursts of precipitation, that the fronts are more associated with the low level, lower precipitation rates. I don't know.
The question is, what's the mechanism for all of this precipitation if it is not, fronts in some sense?
So the QBO small at the short period, does that indicate the acceleration rate is already too large?
Yeah, I think so. That's what I was trying to say. Let's see. Here. So.
Right. So if you further increase the resolution and you have more gravity wave forcing, will that make it even bigger?
Well, then the hope would be that you could tune down the parameterized gravity wave drag, and you wouldn't need to rely on that as much. And so, yeah, what I was trying to say is that it already looks like the parameterized gravity wave drag could be turned down a little bit, and there's evidence that because the period's a little too short, and the total forcing from the gravity wave drag and the resolved waves is actually, 1.5 times larger than what the MERA 2 suggests it should be. Unfortunately, in practice, when you go in and double the vertical resolution, it doesn't work out so easily, and we're still working that out, I think.
I remember Kalatani has the same problem. They have a very short period, but
Yep.
they don't have parameterization.
No.
Everything is resolved.
Right.
So you would think that the period will be shorter if they resolve more waves.
Yeah, I think, but in this case, it's the parameterized waves that are so strong.
Are there more questions? Let's thank Laura again. Thank you.